All right, here is your lesson for inverse functions, and this is the last piece of our function unit. So you will find that you'll have your test on functions next week. So what is an inverse function? So what does the word inverse mean to you? So here's sort of a formal definition of what an inverse function is. So we can say that the functions g and the function f are inverse functions such that when we compose the two functions, whatever we input becomes our output once we compose the two functions. So f composed with g of x is equal to x for every x in the domain of g, and g composed with f of x is also equal to x for every x in the domain of f. So we'll go through and do a few examples so that this makes a little bit more sense. And before we get there, I just want to talk a little bit about function notation and the inverse function notation. So we would denote if I have f of x, I could say that the inverse of f of x is f inverse of x. And I just want to make sure sort of this note right here, this is just notation, and this does not follow the rules of negative exponents, so this actually does not become 1 over f of x. So again, this is just f inverse of x, and this is just the notation that we'll use moving forward. So the word inverse to me means sort of going backwards or doing the opposite. You're inverting something, and that's exactly what it means when we talk about functions. And when we talk about functions, we know that every input maps to one and only one output. So when we talk about the inverse of a function, not every function has an inverse that will become a function. I know that sounds kind of confusing, but hopefully once we do a few examples, it will make a little bit more sense. So only functions that are what we call one-to-one functions have inverse functions. So I guess we could technically find an inverse for every function, but that inverse won't necessarily be a function. However, if the function is one-to-one, then we know that the inverse will also be a function. So let's just take a look at this. A one-to-one function is a function that I like to say is forwards and backwards a function. So every domain maps to only one range, and every range maps to only one domain. So if I look here, 7 only maps to 3, 8 maps to -5, -2 maps to 11, and -6 maps to 4. So this is a one-to-one function. There are no repeated inputs or domains, and there are also no repeated outputs or range values. So looking here, determine if the function h is a one-to-one function. I can see that -3 maps to 8, -11 maps to -9, and I can also see here that 6 also maps to -9. So this is not a one-to-one function. So I could technically find the inverse of this, but the inverse would not be a function. So looking at graphs, another way to tell if something is one-to-one, similarly to the determining if something is a function, the vertical line test, the horizontal line test will tell us if we have one-to-one functions. So looking here, again, I can just draw these horizontal lines in my graph and see that I only hit at one value. Looking here, I can draw a horizontal line and I actually end up hitting in 3 different spots. So this is not one-to-one, but this is one-to-one. Moving forward, I can see here that I have, this is a function. Every input only maps to one and only one output, but it's not a function backwards. This 2 and this 1/3 value, this comes from 1/2 and -1/2, and this comes from 3 and -3. So this is a function, but it's not a one-to-one function. This function over here, math and its output, physics and its output, foreign language and its output, English and its output, these also only map backwards to where they started from. They don't map anywhere else going backwards. So now we can talk about how we can find inverse functions. And if I'm given a table, let's call this f of x, since we know this is a function, I can say that x and f inverse of x, all that I'll do here is swap my x and y values. So 64 and 4, 125 and 5. So we talked about the word inverse reminding us of the word invert, or going backwards, or doing the opposite. So that's exactly what we're doing here. We're really just swapping these x and y values. We're going backwards. How do I find the inverse on the graph? We can pick a few key points here. So this is 4, 1. This is 0, 3. And this is -2, 4. And I can go ahead, and if this is x and this is f of x, I can call this x and this f inverse of x. And I can go ahead and plot these, but by doing the opposite. You can see as I'm filling in this table. So over 1 and up 4, over 3 and up 0, over 4 and down 2. And I can go ahead and connect my values here. Great. Moving forward to this over here, right off the bat, I can see that this fails my horizontal line test. So this won't necessarily have an inverse that is a function, but we can still create the graph. We can still find the inverse of the function. So I can do this the same way that I did my other values. So if I have x and f of x, let's say I have 1, 0, 2, 3. I also have -1, 0, and -2, 3. I can go ahead and make my inverse chart. So 0 and 1, 3 and 2, 0 and -1, 3 and -2. And we can actually see as we make this table that 0 would map to 1 in my inverse function, so we won't call it a function. 3 would map to 2, 0 also maps to -1, so we can see sort of visually with the graph and also with the table here that this would not be a function, but we can go ahead and graph it. So over 0 and up 1, over 3 and up 2, over 0 and down 1, and over 3 and down 2. And I can go ahead and connect my graph so that we are looking something like this. And just sort of a fact about inverse function graphs. They reflect over the line y is equal to x. So if I were to come in here and, here, let's pick another color. If I were to come in here and sketch a dashed line here where y is equal to x, we can see that there's really nice reflection over the line y is equal to x for both of these functions. So inverses reflect over the line y is equal to x. And lastly, for equations, how can I figure out what the inverse of a function is? There are a few steps, and since we've talked about going backwards and doing the opposite, I have y is equal to -5 times x minus 7. The first thing that I want to do is I want to swap my x and y values. So step 1 of finding an inverse, x is equal to -5y minus 7. The next thing that I want to do is I want to solve. I would like to solve for y. So here's my y value, and I just want to isolate my y value. Divide both sides by -5. So here I get y is equal to x plus 7, all divided by -5. And my last step is to replace y with function inverse notation. So here I can get rid of y, and I can call this f inverse of x. So thinking about how we're going backwards or doing the opposite, if I were to plug something into this function, the first thing that I would do is I would multiply it by -5, and then I would subtract 7. So looking here, if I would like to undo that function or do the opposite, when I plug something into my x value in my inverse function, I'm doing the opposite of the last thing that I did up here. So instead of subtracting 7, I'm adding 7. And then instead of multiplying by -5, I'm dividing by -5 to give me back my original value. So I'll erase my steps over here so we can move on to the next example. And if you take a look here, this piece right here, if I think about what the graph y equals the square root of x minus 2 looks like, this will produce something that is not a one-to-one function. But if I restrict my domain, or if I restrict my range like they have here, it will produce something that is one-to-one. So it will pass that horizontal line test. So what I can go ahead and do is I can find an inverse function if I restrict the domain here, or if I restrict the range here. So I can follow my same steps. I'm going to swap my x and y, and then I'll go ahead and isolate my y value. So the first thing that I'll do is I'll square both sides to get rid of that square root, and I'll add 2 to both sides. So now I have y is equal to x squared plus 2, or x squared plus 2 is f inverse of x, if we called this f of x to begin with. So here is my inverse function. All right, and one last example to sort of go into a little bit more detail about this restricted domain or this restricted range. It says on the graph here, v of x is given on the grid. Is v of x an invertible or an inversible function? And justify your answer. I would say the answer to that is no, because it does not pass the horizontal line test, so it is not a one-to-one function. Draw the inverse of v of x anyways and explain why it isn't a function. So here I can go ahead and pick some key points. So I have x and v of x. So this is -1 and 1. This point right here is over 0 and up 3. And then I have over 1 and up 5. Let's get some of our negative pieces over here. -2 and up 3. And let's get one more. 1, 2, 3. -3 and up 1, 2, 3, 4, 5. And let's go ahead and call this x and v inverse of x. So 1, 3, 5, 3, and 5. -1, 0, 1, -2, and -3. And I'll just go ahead and I'll plot these points. So over 1 and down 1, over 3 and up 0, over 1, 2, 3, 4, 5, and up 1, over 1, 2, 3, and down 1, 2, and over 1, 2, 3, 4, 5, and down 1, 2, 3. So I can go ahead and connect these lines, and I can extend them if I'd like. And I can come in here with another color, and we can see again, this is a really nice example of this graph very nicely reflected over the line y is equal to x. So explain why it isn't a function. I can see here that for 5, there are 2 outputs. One of the outputs is at 1, and one of the outputs is at -3. So that takes care of A, that takes care of B. Part C says find a restriction of the domain of v of x so that the restricted graph will be invertible. So what I want to do is I kind of just want to take away half of this graph. So if I were to get rid of this piece of the graph and I only examined it from here over. From here over, this is a one-to-one function. So now it says using your restriction from part C, so I can say that my domain of the graph is x values such that x is greater than or equal to -1. So now I can see that my domain of this graph will produce something that is one-to-one. So using your restriction from part C, graph the inverse v inverse of x. So what I can do is I can come back to what I had already graphed over here, and this would be the inverse of what I sort of chunked off of this graph here by getting rid of this part of the function. And part E says find a second possible answer to C, and I could go ahead and chunk off this part of my graph, and I could say that my domain is x values such that x is less than or equal to -1. So those are some examples of inverse functions. So some equations, some tables, some graphs, and a little bit about restricted domains. So when we get into our trig functions later on in the year, the restricted domain will play a really important piece for us.